Good morning, everyone. So for the next coming 40 minutes or so, I'm going to talk about comprehensive RISC-V solution for diversified SoC, for your diversified SoC. So this is today's agenda. First, I'm going to use some example to talk about what I mean by a diversified SoC. And then I would introduce AndeStar V5 architecture, which we think is the best extension to RISC-V. And based on that, I'm going to talk about our 25 series processor, and then supporting environment. And then it's one of the most important technology we think we offer to our customer, and this custom extension to allow customers to using our environment to add interaction to fully explore a RISC-V's potential. Then I'll give a conclusion. So diversified SoC. So through the past 13 years, and this processor has been used by many different customers in different applications. For example, some customers are using less than 16 interrupt, and they will ask who is going to use more than 32 interrupt. But some customer was using our simple core and asking for more than 100 interrupt as an interrupt source. As far as interrupt latency goes, some customers never ask what latency is, but some care very much because they are kind of in the real-time application domain. And regarding media processing or data processing, some require very efficient type of processing like the DSP and SIMD based on existing resources, a general purpose register. The other type is get as much performance as possible, which is probably need to base on scalar vector with additional resource, vector register, separate pipeline, and so on. Cache, we know most people use a write-back cache, but sometimes you got legacy or you have special SoC you really need write-through. We even have customers, they want us to use an instruction cache to put read-only data there because I can share reduce the latency and share the same the SRAM there. And then there's a hardware engine versus a coprocessor, which one is better. And also for a small processor, it could be just the only processor using a simple MCU, or it could be many of them, many instances using large SoC. So they all have different requirements. And also some people like to use open source compiler, GCC, LLVM. They think this is the only thing they have in the world. But they also, another word, they require commercial compiler because they like the ID or different feature. So many different use. So we think that one size doesn't fit all. So and this goal is to provide as many features as customer want. You don't tell them what is best, give them what they need. So AndeStar V5. From the previous speaker, we know that RISC-V ISA, in the technical side, the merit is compact, very small kernel, and modular. You can have a lot of different extensions can add it on that. That's kind of standard extension. But the most important thing, I think, is the freedom of custom extension. So you can add the instruction you need based on for your application, to speed up, to do reduce the power consumption, and so on. And this comprehensive solution is all based on custom extension. Some people will start to think, okay, if people start to adding extension to RISC-V, would that cause fragmentation? Actually, it's already well thought out. So Kirsty Sanovic, the chairman of RISC-V Foundation, Berkeley professor, and Sci-Fi founder, has an article in a recent E-Time. He said RISC-V was designed to support specialization while avoiding fragmentation. So how do you do that? Basically, you need to follow the common ISA and use that as standard to build a software ecosystem. But you still need to leave ample space for innovation based on the extension. So we think extension is the key to advanced RISC-V. Again, standardize on the common baseline, using extensions to build what you need in the application, and maybe eventually most popular extension, a custom extension, will come back to become a standard. So this is a good way to move ahead without having a committee discussing every little thing and slow down everyone. And this has been building our comprehensive solution based on processor, architecture, so on. So for RISC-V, We started with our V5 architecture, which we are going to talk a little bit more on the next page. And based on that, we built our processor, which is highly optimized design, and we envision that it's going to be used for a long time by our customer and by we continue licensing to more customers. And we have a very rich peripheral IP and development board, and we also have professional ID, which will provide a very good user-friendly environment, and also, most importantly, high quality of the code and extensive software stack. So Andes all built around that. We know customers have more choice. So in addition to what we have, Andes also work hard and work closely with our partner, and our goal is to grow RISC-V ecosystem. So we want to work together to take RISC-V mainstream. So what is AndeStar V5 architecture? It's a RISC-V standard plus Andes extension. So what we added here? For example, we added the baseline ICE extension. For example, in the baseline RISC-V, you need 2 instructions to do the memory access and 2 instructions to do the branches in some cases. And we have 1 instruction to do that. So faster memory access and faster branches. And RISC-V's C extension produces very good code. But we have additional instruction and compiler technology to allow to provide even more compact code size. So we're going to show you some data later. So this baseline ICE extension is provided through our compiler, so you don't even need to be aware of that. And so, but that's kind of more for general environment. And customer want to have different application. They want to add the instruction to speed up the application, so-called domain-specific architecture or domain-specific extension. So Andes offer a powerful tool so that your design team don't need to have CPU experience, and you can add instruction to achieve that goal. So this is Andes instruction, and then provide baseline and also tool for customer. And we also continue to kind of push down the RISC-V standard. In the last 4 years, Andes is a very popular core based on DSP, SIMD instruction, that's on our own instruction. And we moved that over to RISC-V as a starting point for this P extension task group. And we are running the task group as a chair. And so this is based on a general purpose register, so it's very efficient. Beyond the instruction extension, there's also privilege space, which is also very important. For example, in the past, we know that customers need full cache support, starting from management instruction like flash, invalidate, and so on, and at cache line level of granularity. And some people need on-cache access. Not everything needs to be coherent by hardware. They may want to have the choice of managing that by software and write back and write through. I talked about that earlier. So we make that all possible through our extension. And also, PRIC is RISC-V's platform level interrupt controller. It's a lack of vector dispatch and priority-based preemption. So we enable that, and that allows to reduce 50% of instruction before you reach your C code for a general interrupt service routine. And we already, because of our discovery of that, this vector extension, so right now we are kind of pushing the fast interrupt task group together with the Sci-Fi, so we are co-chairing that task group. And so hopefully that will become kind of the standard, so people can share the invention that we found. We also want to talk a little bit about the state of RISC-V software, which Andy is also very active on that. We know that GCC, NewLib, and glibc is also already available, and Andy is a co-maintainer of GCC and maintainer of NewLib. And 64-bit glibc, Sci-Fi kind of put that together, so we have 64-bit Linux, debugger, GDB, and OpenOCD. But there's no 32-bit Linux supported officially yet, so that Andy is kind of pushing toward that, starting from the glibc. And so we're making very good progress there. So hopefully going to go to the main line very soon. And Andy is also active in LLVM compiler. So we donate the first workable compiler with optimizing set. Then we can work with low risk closely to kind of push that, and also a little bit of Berkeley. So right now LLVM needing 64-bit support is in the reviewing the progress, but they're still missing half floating point number calling convention, but it's kind of already very good for the integer part. Compiler, the runtime, and also LLD is LLVM linker, which Andes also can donate porting of that, and it initial set already supporting non-Linux environment, so it continue going down the road. So dynamic linking right now kind of in the review process. Give you a data. So if you take the best GCC result and LLVM result for Embassy, you can get 20% improvement. So, and there's up and down, sometimes LLVM better, sometimes GCC better. Right now, most of the time GCC better, but LLVM also better in quite some categories. So if you take both compiler and this over today, so you can get 20% higher performance than just using GCC. Okay, Linux and friends. Andes contributed the U-boot, Sci-Fi contributed a 64-bit kernel, and then Andes kind of covered the key utility for Linux because that's very important for you to tune the performance of Linux system. And then, like I said earlier, we are kind of pushing the 32-bit Linux kernel, and it's already accepted. And now that GDIPC, once GDIPC ready, then everything will be there. Okay, so AndesCore 25 serial processor, or V5, this is based on V5 ISA. So if V is for 5, V5 is 25, so that's how we get 25 series. So the common feature, we're going to talk about that first, including 32-bit and 64-bit version, and it starts from scratch to get the best PPA. We didn't take it from open source from anywhere to start it because we designed the processor for the past many years. So we know how to do it in the best way. So the baseline ISI is based on RISC-V's IMAC, and then we add on top of that. They are all 5-stage pipeline, single issue, very simple, efficient pipeline. We reserve one full cycle for the critical SRAM, like instruction SRAM, data SRAM, so that its frequency can reach the traditional 8-stage pipeline call. And we only using single-ported SRAM, so it's very power efficient, small area, but with a little bit control code there. And multiplier, so we have a sequential multiplier. It can produce 1 bit per cycle to 8 bit per cycle, depending on how you want to configure it. But if a multiplier is very important for your performance, then you can configure with a parallel multiplier, which will be pipeline and finish in 2 cycles. And also have branch prediction with all the important feature, branch target buffer, history table, and also return the stack. And for the memory subsystem, we have both. The user can choose local memory and or caches. The local memory is a fixed latency memory. You can configure it with a very wide range of size from 4K to 16 megabyte. Using the interface for SRAM and also HB Lite. HB Lite interface is provided so that it can drop in replacement with Cortex M3. And caches has a size from 8K to 64K and direct map all the way to 4-way. And if you need to have high reliability for your SRAM system, and error protection is optional with parity or ECC. And the bus interface side provides a standard master port, HB or AXI, and it also has slave port coming in, so you can access your local memory. And standard JTAG debug module with up to 8 trigger. And trigger is watch point, breakpoint in the RISC-V terminology. So 25 series, we have 6 of them. N25 is 32-bit and X25 is 64-bit. They are positioned as fast and small core used for control tasks in AI, AR, VR, networking, storage, and more. And N25F and NX25F is with a floating-point addition. You can choose a single precision, which is F, or single plus double precision, FD. So they all have a very efficient 5-stage pipeline for all the important instructions: addition, subtraction, multiply, add, multiply, sub, and divide and square root take longer cycle. But they are not as used as often, and once they're executed, they'll be put in the background so the processor can continue to execute a new instruction. So A25 and X25 are with floating point and Linux extension, supporting RISC-V standard MMU and super user mode and all the different virtual addresses and the page size. And in the microarchitecture side, we implement 4-way up to 128 entry of shared TLB, and also 4-8 entry micro TLB for instruction and data. So here's some floating point number based on. So blue one is single precision, red one is single precision, blue one is double precision. Here we compare N25F with dual issue, Cortex M7 and Cortex A7. So in the double precision side, you can see that N25F is more than 2x of the other 2 core. and single precision side at least 20% faster. So now let's look at some hard data. So this is for TSMC 28 nanometer. So the smallest usable configuration for N25 and X25, that is configured with local memory, no caches, no BTB, which is consume more resources. So at 1 gigahertz, both can run at 1 gigahertz, and N25F just consume 37 kg and 0.033 millimeter square and 4.1 microwatt per megahertz. And 64-bit version is just a little bit larger, consume a little bit more power, but it's very compact. And down there on the table is more full configuration. So with 32 kilobyte instruction and data caches and 256 BTB, and also a single double precision floating point, and with MMU or not. So you can see it across wide range of the feature. And the worst case frequency can range from 1.2 gigahertz to 1.4, depending on which one you are. And they all have leading Comark and Drystone with very good number. And again, this is based on 28 HPC plus, real RVT, and Nitrate library. And when we ship out RTL, we also provide configuring tool. So this is a lot of things we talked about that earlier. So you can, for example, select whether you want A instruction or not, atomic instruction. A lot of privilege mode features are kind of optional, so you can select that. Perform monitor, or a couple features that end is kind of extended. In the bus type, you can select HB, XI, 32-bit, 64-bit, and multiplier, branch prediction. And this is for local memory, IND, and caches, and debugging support. So very easy. So you just select what you want, and then you have your RTL configured. So it's going to generate a header file for you, and then you can use that to build your simulation and synthesis and so on. So here I want to kind of add some summary for this advantage of 25 series processor. So Andes N25 is 5-stage pipeline. So we compare with open source code, which is also 5-stage pipeline, and using Foundation compiler, Foundation GCC, which Andes is also a major contributor, and for the 32-bit one. So our Comark is almost 9% faster, and DMIPS is 6%. But if you use Andes compiler, which is on rightmost column with V5, then you can get over 20% faster in Comark and DMIPS. And CSAP is a very popular code size benchmark, including audio library, JPEG library, compression library, and so on. So using Foundation compiler for OS, it generates 1.3 megabyte of code, but using Andes V5 compiler with Andes instruction, you get 12% smaller code size. So this is code size is sometimes very important for certain customers, especially because this could be kind of affect their die size. And there's also some rich feature for embedded application we talked about earlier. It comes with a complete feature for caches. And one thing that we have mentioned before is we support hardware misaligned access, because we think majority of code today running on x86 or ARM, so people probably use that to do prototyping. And when they move to RISC-V, I think most people today, when they get misaligned access, they just trap and use software to emulate it. But ARM and x86, they directly execute that on hardware. So if you're lucky, you don't have misaligned code, that's okay. But once you hit misaligned code, you're going to be everywhere. So emulated by software is going to give you very bad performance. So Andes learned the hardware about 5 years ago. So after that, we basically make this default in hardware. So we have that. Stack safe, step protection, a very good feature, and also supported by our IDE. For the embedded software, can kind of help you to protect your stack without kind of overflow or detect that for you. We have power management feature, and we also already had the fast interrupt handling maker that we talked about earlier, but we want to make that foundation standard. For the small with a pin limited chip, a 2-wire debug support is very important. So we have that too. And also we have better Verilog RTL code. Since our RTL is written by human, so it's very readable. Some vendor, their RTL is generated by high-level language. And when you generate the code, it's very difficult to read, very difficult to understand it. And when you go to CAD tool, because human written code is going to have very good coding style, so CAD tool is much easier for CAD tool to optimize it. But tool-generated code has trouble for CAD tool to kind of fully utilize that. And also we provide a configuring tool so customer can configure it at their desktop instead of asking vendor to configure for you. Some users think configuration is very important, very proprietary information they don't want us to know. So we give them a tool so they don't need to tell us. They can do that by themselves. Okay, supporting environment. So in addition to the processor itself, here you can see the pink range. That is we call a CPU subsystem. So you need a processor and platform level interrupt controller, also debug module. It's arranged this way so that when you have multiple instances, debug module and PRIC can share among them. And beyond that, we also provide pre-integrated platform for our customer, which include HB or AXI bus matrix, and also corresponding DMA controller. And then we have a HB bridge connected to a series of very useful low-speed devices. Everyone probably can do that themselves, but this is something which our customers have been using for many years, so very efficient and have a lot of good support there. So this pre-integrated platform to help customers to speed up their development of SoC. And we also have provide our ICE. You can buy the standard USB JTAG ICE, probably named for ARM, but actually there's nothing to do with ARM. You can just using proper software to use that, but you can also use Andes provided tool, which had better download speed. And AndeStar is our professional IDE, so it's Eclipse based, but it's followed by our 13-year development. So we have very good talk in the afternoon to give it more deep introduction. Most people probably just say their IDE based on Eclipse, and next page they talk about something else. But we have 30 minutes to show you in the afternoon. As far as the development, target development environment, we have physical board, the large one, which is full feature, different component there. And we also have a smaller one, more compact, Arduino footprint, which is come with AL2.15.4 and is ICE on board, so you can use that to develop some kind of IoT development, prototyping software. And that's kind of physical board. And we have simulators supporting this in the AndeStar, the IDE, a new cycle accurate. So it can run as standalone mode, and can also run in system C, TLM environment. So people who like to do the large system level development, prototyping, and can be used for that. And any GDB remote capable simulator such as QEMU can hook up to our IDE. OpenSUSE project already can take our QEMU environment with X25 platform to develop this UEFI firmware environment. And we have software stack start from the bare metal environment. We provide very rich sample project, Andes, and also RISC-V standard feature so that customer can kind of get up to speed very quickly. And Autosys, and we also has IoT stack to show you how to connect it to the cloud. Okay, and this custom extension, what it is, what it look like. Here is the overview of it. We provide customer with RTL, simulator, and all the development tool, which is ready to be extended. So how do you extend that? So you write concise Verilog code for to eventually map to RTL, and a C code for the behavior, and then you use attribute setting to tell tool to do some information, so tool can do a lot of work for you. So you can, based on this framework, you can design scalar instruction, vector instruction. Instruction can run on foreground or background. You can have wide I/O, so you can get very wide data and do the processing and write it out. And we provide a tool, COPILOT, to help to do a lot of transformation for you. So it will generate extended RTL, extended ISS, and extended tool component based on the description by user. Together with the baseline component, you got the new environment for your new processor with RTL, simulator, and the tool. The tool called COPILOT, the design itself is a pilot. So the tool is just there to help you to automate the housekeeping test. And one thing that people would concern knows is that if you add instruction to the processor, how would you affect the pipeline? How do you do the verification and so on? Our framework kind of all taken that into account. So we have this automatic environment for cross-checking based on the generated extended RTL and generated extended ISS. So we kind of mix that together and generate a test pattern, and then we do cross-checking for you. So very automated. Jumping to a little bit complicated example, but just to show you the powerfulness of the ACE environment. Inner product is very important in machine learning application. So let's say when you do inner product, There's one component less change, and it's kind of constant, and the other one is vector. We kind of keep changing. So for the less change part, you probably can put that into registers. So we define something called coefficient register on the left-hand side. It's 4 entry, and width is 512 bits. And the other one keep changing in the inner loop. We put that call that as vector, also 512 bits. So ignore about the other guy. And so you want to do inner product of this 512 bits, which is 64 of 8 bits data. So once you define the data type, you can define the input-output of the instruction. So one of the input is C, is from coefficient register. The other one is V from the vector memory. And the inner product is about 22 bits, so you can put that into GPR, which is general purpose register. Let's look at Verilog part, so much easier to understand. So C and V are 512 bits. So you're using Verilog way to extract the corresponding bits and do multiplication, and you write 64 of them and add them together. Now that's all you need to do. Later on, we're going to make this tedious work of writing this 64 times less painful. So what about the C code, C simulator part? And because C doesn't have a 512-bit data type, but we include multi-precision library so that you can do that. So you can treat C and V just like 32-bit data. So we shift it to the right and extract the bits, do the multiply and accumulate into IP, just like what you did on Verilog part. So with this, the tool can generate the Verilog part for you and hook it up to the processor, and on the other part, the left-hand side actually generate everything for simulator and all the information needed for the tool. And so with this instruction, you can get 85x speed up. So the tool also will help you to generate so-called intrinsic function, so you don't really need to use writing assembly code to use the instruction that you generated, which is down on the bottom on the right side. And to help, this case is relatively easy, but if you want to do something more complicated, in the AC begin and AC end, you can have the Verilog syntax like always and so on, state machine. So you get more complicated, you probably need some time, something to help you to do debugging. We automatically generated a waveform control file, so you can easily see the operand and other signal defined inside your module. So the benefit of AC is that user only focus on instruction functionality, not CPU pipeline. All the housekeeping tasks are generated by COPILOT tool. For example, we never talk about OP code selection, so you don't need to worry about that. We'll find the best OP code position for you, and also the instruction mapping. And so once we do that, so the tool can automatically generate instruction decoding Verilog, and also for code for simulator, operand mapping, and how do we get the input operand, and for output operand, how do we do the update, and dependency checking with the previous instruction and the instruction afterward. This is all done by the COPILOT. So all done for Verilog, or RTL, and also for simulator. So this is a very good way to help the customer to design the instruction. And after we have this tool, so adding instruction is more like ASIC design. You don't need a CPU expert or anyone with CPU knowledge. So conclusion remark. First, I want to talk a little bit about our processor roadmap. So right now we have a 625 series processor, and we are continue developing the P extension, the DSP extension, and also cache coherency multi-core up to 4-core. Then after that, we're going to enhance with vector extension. So this is kind of a 5-stage pipeline. So we're going to go up to get 2x performance with the new family, and also go down with half of the area and power, and more like 1/3 of that. And for the small core, we call Bumblebee. It have baseline core, and then it will come with AC support, P extension, and floating point. We envision it used as the only processor in a small chip, or using many instances in a large chip. For 2x performance, we call Aries. So we're going to have unique single core and also multi-core, just leveraging the multi-core environment which 25 series will generate. And later we're going to have optimized multi-core for Aries. So Ande provide a comprehensive solution for RISC-V based on our rich SoCs experienced in the past. And starting from the V5 architecture, we think the best extension to RISC-V, and come with good support. And 25 series processor, fast and small version for control task, 14-point core for compute intensive task, and also to help AI to do the alongside with the accelerator to do the kind of housekeeping task. And A processor is targeting for application processor, entry level one. And we have powerful ACE and COPILOT tool to unlocking RISC-V potential for domain-specific architecture. And we have strong tool and software support. And the continued roadmap is to intend to serve a broader market. And this is a focused and pure-play CPU IP company for 13 years. So we are intended to continue to be here to focus to serve your need for CPU. So we like to be your trusted computing expert and your best RISC-V partner. Thanks for your attention.